This is a demonstration of the effects of broadband radio frequency interference. This was the first kind of RFI that was experienced. It arises from rapid changes in voltage or current in typically electromechanical devices. Unintentional sources would be brush noise in generators or motors, and an intentional source, so to speak, would be the ignition system of an internal combustion engine. For our demonstration, we have our victim radio on the right. It is tuned to a frequency in the AM broadcast band, which historically has been very susceptible to broadband RFI. And on the left, we have a simulated spark ignition system, which consists of an old 461 CS06 spike generator driving a special step-up transformer that can put out kilovolts and drive the spark gap that you see there. Before we home in on the spark source, I bring your attention to the electric field probe that is parked directly behind the spark gap, and its output feeds the antenna input of the radio victim, and that also tees into a Rhodian Schwartz FSV spectrum analyzer, which we will later on be using to visually inspect the broadband source that we're going to be listening to momentarily. And now we enable the spark gap. And disable. And up close and personal. And off. Now we're going to sequentially bring up the spark gap and then turn up the volume on the radio so we can hear the effect on the radio. We could hear both the actual spark itself and the effect on the radio. Because we're mainly interested in the radio, what we're going to do next here is we are going to turn the spark input voltage down, that is the input to that transformer, until the spark gap just doesn't jump. At that point, we'll still have plenty of voltage and voltage rate of change at the spark gap. We just won't get the spark and hence the consequent audio. And we'll be able to concentrate on just the RFI effects from the radio. Now we're hearing just the radio, and as I varied the rep rate of our simulated ignition system, what you heard was called motorboating for obvious reasons. It's what you hear if you have a poorly suppressed ignition system on an internal combustion engine. Now we're going to bring up the spark ignition source, less the spark, and listen to it at our tune frequency of 770. Then we're going to tune across the band and see what it sounds like at different frequencies. First we'll tune down from 770 towards 530, the low band edge, and then we'll turn around and go back up and end up at 1710 at the high band edge and kind of gauge the effect on the radio. So here comes the spark source. There's our motorboating. And this radio can actually tune in 1 kilohertz steps, even though AM broadcast stations are every 10 kilohertz. Now you can see we're stepping down 1 kilohertz at a time. That's 10 kilohertz off. Now we'll just drop to 750 kilohertz. No change. 740 kilohertz. Let's go to 700. Let's go to 600, 530 band edge, no change. We started at 770. Let's go the other direction. Let's go to 800 kilohertz. Nothing different. 900. Let's go to 1200. Let's go to 1600. And let's go to 1710. All right, let's turn that guy off. So the upshot of all that is that we tuned clear across the AM broadcast band, and we found that broadband noise everywhere, hence the name broadband. What this leads up to is that when your predominant sources of RFI were in fact broadband, it was sufficient to tune to a couple, 3 frequencies per band to gauge whether or not there was a problem in that band. So if there was a problem, because it was splattering all over, checking a couple, 3 frequencies would suffice to find it. And if you check those couple, 3 frequencies and there was nothing there, it was a real good indication that the entire band was clean. Now, as a practical matter as to how you would go about doing this, there's fun ways, or maybe not fun ways, but certainly there's less painful ways. So although this radio does not have a traditional squelch circuit, we can use the RF gain switch to simulate a squelch circuit. So I'm going to go ahead and put this thing in the highest sensitivity mode called DX, which is essentially no squelch. And you can hear that background hiss. Now the purpose of a squelch circuit is to eliminate that background hiss, and that's in our medium situation right here. And the point is that if you're tuning along and you've set your squelch so you just don't hear that background hiss, and as you tune along, suddenly you run across this, where you broke squelch, that breaking of the squelch was your fail criteria for having found RFI when you had set the squelch up to be just above the background noise. Okay. That's actually described in Mil Standard 464 not as something to do, but as the way things used to be done. And then it goes ahead to tell you why that doesn't work anymore, which is, of course, the subject of this series of short video demonstrations. And the bottom line is that when broadband sources were predominant, it was an excellent way of doing things. But as broadband sources faded away and narrowband sources became predominant, that's when something new a new technique had to come along.